We're continuing with review, and this is an example with modeling with mathematics. So calculus, there are a lot of discussions with rate of change and how things are related to each other. Rates of change are related to each other, and this question actually brings up some of those facts, the precalculus of the calculus concept, basically. And so an observer is viewing the space shuttle take off from a distance of 16 kilometers from the launch pad. The shuttle travels straight up with constant speed of 8 kilometers per second for the first part of the ascent. Let t be the time passed in seconds since the shuttle has been launched. Let theta be the angle of the elevation in radians. And so this is the picture that's so somebody's over here and observing the shuttle go up. This can be a cameraman, and he needs to know, he knows the speed of the shuttle, he knows his distance from the launch pad, and he needs to figure out the rate of change of how to raise his camera so he follows the shuttle, basically. We're actually simplifying this problem, and but that's the eventual problem that we end up in calculus, basically. So the first part of the question here is express the vertical distance of the shuttle h as a function of time t in seconds. The constant speed 8 kilometers per hour per second, and that means that the speed is going to be the height is going to be the constant speed times time passed, because it starts at height equal to 0 and goes up. Now, the second question, express the angle of elevation theta as a function of vertical distance of the shuttle h in kilometers. Okay, so this one was something we knew from the past, how to relate the constant speed to the distance traveled, and that in here h is the distance traveled. Now this part of the question is asking relate theta and h. Theta is over here and h over there. We know from trigonometry that I have a 16 miles or kilometers over here, and I can use the ratio between h and 16 to find a ratio for a trigonometric ratio for theta. And so that would be tangent of theta is equal to h over 16. And so I use that first, but this question is asking to find theta as a function of the vertical distance. I related theta and h and no other variable in here, and that's the first part that I want to do. Now I want to solve for theta, so theta would be a function of h. And solving for theta, I get theta of h. Do you see over here I had h of t, then is h as a function of t. T is what the input is. And here is theta of h, and h is the input, is equal to arctan of h over 16. Over here I basically solve for theta, and then I remembered because theta is going to be a function of h, I use that notation of parentheses h in there. Now, the next question is express the angle of elevation theta as a function of time t. Oh, we just did express theta as a function of h. Now we're actually finding, let's see, it was theta of h and I had h of t. Oh, so if I want to express theta as a function of t, I need a composition of the two functions, is theta of h of t. And so that's what happens. The composition of function becomes arctan of, instead of h, 8t, 16, right? It was h of t, so it would be basically 8t. So the next question is, what is the vertical distance in kilometers when t is equal to 2 seconds? And I look at this part, that's the vertical distance, h in terms of time. I plug in 2 in here and I get 16. The next question is, what is the angle of elevation in radians when t is equal to 2 seconds? And I look, and angle of radiation, theta, as a function of time is right here, so I can plug in 2 in here, and I get theta equal to arctan of 8 times 2 divided by 16, and that is pi/4. So one thing that we want to, before moving to the next part of the question, next example, is to notice this. When you relate theta to a function of time, or when you relate theta as a function of height, this relationship in calculus, you can also relate the rate of change of theta to h or time, either one. This is how you calculate that rate of change in theta, and then that's, let's say, someone with a camera is standing there and trying to keep up with the shuttle. That person needs to know how fast theta is increasing, and so that's how you figure it out in calculus. And calculus part of it is another technique, but this part of the pre-calculus part is how things get together and make sense together. Example modeling optimization. In pre-calculus, there are a few functions that we can optimize using either algebra or trigonometry. One of them is the quadratic function, and we're kind of expecting this because it's part of the pre-calculus review. It's supposed to be a quadratic equation. And so the question is asking, what is the maximum area of a rectangle inscribed in a right triangle with side lengths 3 and 4 if the sides of the rectangle are parallel to legs of the triangles. So this is the picture. Picture looks like that, and let's think about it. If I move this x and y point, the point that is on the hypotenuse, then I get different size triangle. So let's try that first. See, over here, I can move this point and see triangle still inscribed, and the rectangle still inscribed in the triangle. And so over here, the area is, it's a very long rectangle, and area smaller and smaller, and then somewhere around here 3, and then becomes smaller and smaller. And so remember, the area over here is actually rounded, and so we don't have the precise number, but it seems like over here it's smaller, over there it's smaller, and it gets bigger around here. So let's see, let's algebraically calculate this and figure out what the value of the maximum area is. So one thing in here is I look at this rectangle, and I see there are 2 sides of it. To make things a little easier, and sometimes we don't take the exact side of the or exact variables that are involved in the optimization. So let's see what I mean. Here we're maximizing area. Maximizing area is this length times this length. And there are two different lengths, and therefore the function we're optimizing is function of two different variables. One thing is that we're not equipped to deal with functions of two variables, so we have to convert one variable to the other variable. It turns out that it sort of calculation-wise, this one's a little easier, and I recommend trying to actually consider this side to be x instead of having this little length to be x, and see how the calculation becomes a little bit more algebraically complex if you switch the x. But if we have to find a way to relate this length to that length, and then basically solve for y or x in terms of the other, and that way both variables and the function are going to be the function is going to be only a function of one variable. And so how do we do that? That's using something called constraint. There's a constraint in your optimization, and the constraint in here is that the rectangle is supposed to be embedded in the triangle. How does that create a constraint? And so when you embed this rectangle, you see that there are two little triangles forming right there. Noting that both this triangle has the same, it has a common angle with the big triangle, and another angle that is the same, the right angle over here is the same as the right angle over there. The little triangle over here is actually similar to the big triangle over here, and that similarity gives us a relationship, a constraint between y and x, and solving that constraint gives us, I can solve y as a function of x. Again, x is just the 4 minus the length, that is this length of the rectangle. It's right here, this area, this side. So let's do the similarity of triangles. This is the side y. Y over x should be equal to 3 over 4. And that's y over x is equal to 0.75. Solve for y. Y is a linear function of x. It's 0.075x. Now, a is y times 4 minus x. And so you write it like that. Again, two variables input, not good. So what you want to do is you want to write a as a function of x. Again, this is not a times x. It's a as a function of x. And so you replace y by the function that you found from the constraint. And you get 0.075x times 4 minus x. Then you can basically distribute that x inside to get 0.75 times 4x minus x squared. This is a parabola. And we know that parabola, and what kind of parabola? Look, the coefficient, what is coefficient of x squared? Coefficient of x squared is negative times that's 0.75 multiplies through also. And so it's negative 1 times 0.75. And this negative coefficient, negative coefficient for x squared means the parabola is looking downward. Therefore, parabola has a maximum at its vertex. Find the vertex. What is the vertex? And find the domain and make sure that basically the parabola is achieving its maximum within the domain. By the way, the domain is bit 0 and 4 because the smallest amount x can be is 0, the largest that it can be is 4, and that's when the area is going to be 0. And with discussion of the downward parabola, and the vertex is basically, see that 0.75 multiplies both of them, so I know it's going to simplify, and so vertex is going to be the coefficient of the x, negative coefficient of the x, divided by 2 times the coefficient of x squared, and that's negative 4 divided by 2 times negative 1 is equal to 2. So x equal to 2 is the x of the vertex, and it should give us the maximum area. So I plug that x back into the area function and I get 3. That's a maximum area. And so that was how we use the information that we have from the vertex of a parabola to find to maximize this problem. We will have other tools in calculus to maximize other functions, to find the maximum of the other functions. Now, I click here question 4. Use the identity sine of 2 theta equal to 2 sine theta cosine theta, and find the maximum value of the function, and the function is f of x equal to 6 sine of x cosine of x, and take a little break and solve this problem and come back. So I am trying to use this identity, and over here I see I have a sine of x cosine of x. Look over there, I can write sine of theta cosine theta is equal to divide by 2 1/2 of sine 2 theta. And so in here I also can do the same thing. I can write this function as 6 times 1/2 sine of 2x, and then this is 3 times sine of 2x. So when is this function maximum? When the sine is maximum. And when does that happen? When sine is the sine of the angle is equal to 1, and so whatever the angle is inside, and that's when the sine of that angle is equal to 1. So the answer to this one is going to be C, because 3 is the maximum value of the function. If the question was asking when is the maximum value achieved, then you have to solve for sine of 2x equal to 1, and that will give you that 2x is equal to pi half plus 2k pi, and then that is x is equal to pi fourth plus k pi, and then x is equal to pi fourth, and so there pi fourth plus 2k pi are the values that gives you the maximum value for the function, but the maximum value of the function itself is 3.